Welcome back to our lecture series on automated machine learning. We are still in the age of foundation models. Now we're looking a bit more specifically, can we learn how to do HPO with sufficient data? What does it mean actually if we can learn to do HPO? Motivation is that traditional HPO methods, for example, Bayesian optimization with Gaussian processes, target to transfer knowledge across tasks with different configuration spaces or hyperparameters. And I really would like to emphasize here with different configuration spaces. Of course, if you're staying within the same configuration spaces, hopefully you already know what kind of swarm starting transfer techniques there are. But if we really go for other spaces, everything gets much more messy and harder to do. The opportunity is to use massive and in practice, it's proprietary amounts of in the wide tuning data. So for example, Google with Google Vizier has a service running, or other companies in addition to, I guess Amazon and I don't know, preferred networks with Optuna, maybe similarly, have a lot of internal data in how optimization is done and how, for example, Bayesian optimization is applied. And so we can try to leverage these kind of amounts of data. The proposal here was using a transform-based framework that learns a universal prior from vast, diverse offline metadata sets to solve new optimization tasks. And I focus a bit on this idea from OpFormer from Chen et al. 2022. The idea is more as treating HPO as a sequence modeling problem, and we're using an encoder-decoder transformer architecture. It allows us to have a universal interface, so we take unstructured data from, for example, metadata, search-based definitions, algorithm descriptions, and optimization history as input. And then we output a probability distribution over next parameters of function values. And I should be here a bit more clear. I'm sorry. Should be hyperparameters, of course. And so what we're doing is more or less, we don't have an explicit optimizer anymore doing this kind of what should be the next subparameter we should try, but the transformer is directly telling us. And the transformer is really learned as a policy from data from what we have seen before. And so we can see it as a function prior for the performance prediction. Of course, there are some small tricks if you'd like to do that. First of all, of course, we're treating metadata simply as a textual description. That's the easy part. We have parameter names there, types, constraint maybe, and everything is compressed into tokens. Maybe a bit more complicated is that typically our history data, which we're always assuming we have, and also more OpFormer is seeing that over time, more of that, we need to feed into the transformer, and for doing that, we need some kind of quantization. And what they, for example, doing is quantizing that into integers between 0 and 1000 with more standard equations. And then having that more as the history you always have. That is more or less how an example could look like. So really like here we're doing ConfNet on CFA10, the metric is SQC, we would like to maximize. That's the parameters. So hyperparameters actually, and then we have different kind of triads. Sorry that I'm sometimes here writing parameters or that graphic shows parameters because the original paper unfortunately talked about parameters, which are actually in fact hyperparameters. How to train that? We maximize the weighted log likelihood of the optimization history given the metadata and previous history. So that's important more than saying, would like to predict now an entire history given many other histories so that we have seen from before or steps from before. And going with that. So the example of data sources are also more or less partially available. Of course, Google Vizier is not really there, but OpFormer, for example, was trained because it's also a Google paper. But there are things like HPOB, which has a large amount of data, or BOB, you can, with this very artificial synthetic function, you can easily generate quite cheaply actually new directories and history information. And then what this more is doing is that we should not only learn one very specific HPO algorithm. Of course, we could do that in principle, but why doing that? So it would be much more nicer to say we imitate, let's say here at least 7 distinct HPO algorithms. These are from evolutionary algorithms, Bayesian optimization, hill climbing, and so on. And what we can do is in the metadata, simply conditioning then our transformer on one very specific kind. So more then the transformer is not only learning one, but you as a user can actually even choose what you would like to imitate and seeing what performs best. At inference, the model acts as a policy prior to generate new hyperparameters. So it's an autorecursive generation. Hyperparameters lambda t, so the as t's iteration are sampled token by token from the learned distribution, which is then multiplying all these kind of probabilities for the d's hyperparameter in iteration t, given everything we have seen before. So this is more as the policy approximates the behavior policy p by seen in training. So it's behavior cloning what we're doing here. The important thing is we would like to nevertheless outperform imitated algorithms, right? We not only want to imitate it itself, it would solve us maybe a bit of overhead. For example, we would not need to optimize the acquisition functions of BO algorithms, but we would like to go even beyond that. So what we're doing here, we have a function prediction idea. So the model predicts the function value distribution for any candidate in addition. So for any candidates which is sampled more or less from what I've shown beforehand, we can now try to, in addition, say, okay, how well should it perform? And then we can say, okay, we're using, as always, an acquisition function like EI, and then doing more or less, we sample candidates from our prior, this was the last page, so that is really like the transformer model. And we can say that more or less we're sampling that maybe even from different kind of imitated algorithms. So maybe the prior we're doing that from EA, from BO, from hill climb, whatsoever. And then nevertheless using EA to decide what is the most promising one. And that idea helped Opformer with this EI to significantly outperform many baselines and these fully imitated policies actually. To sum that up, we're using here algorithms more as a data source, right? So we have optimization algorithms, which we discussed before, and by running them over and over again, maybe with your customers or maybe on artificial problems, we should keep track of these very valuable information to leverage that. And then train a transformer model, put that more in a text representation, and learn one very big transformer model to go with that. And then we say, okay, transformers can effectively transfer knowledge from offline byte data to improve online optimization efficiently. In the best case, really go to the entire end of the horizon and directly say, okay, if I've seen that kind of history, what should be the most efficient point I will see in the future? Nice thing about scalability is that inference is faster and more scalable than traditional Bayesian optimization methods for long try histories, because we don't have more or less GP anymore in there, so we don't have a cubic complexity in that. Of course, one needs to know that if you're using a transformer and we're keeping everything, we are still quadratic in complexity, but it's better than cubic. With that, I hope you have a new view on how to go with data, which we might have anyway, or at least certain companies have that, and building on that, building even better optimizers which are now data-driven. See you in the next videos.